In normal operation, a Unix system has many programs stored in memory at the same time. The Unix kernel is responsible for switching between these programs. Note that I'm going to use the term Unix for all the systems that have Unix as some sort of ancestor. And these include things like Linux or all the Apple systems. A Unix system is the basis for the Mac OS, iPad OS, and the Watch OS. Apple TV also uses it. So I'm going to use Unix as sort of the generic term for the operating system. Now, the combination of the memory occupied by the program and all of its state, which also includes details of what files it has open and what user is running the program, and so on, that's called a process. And I'm going to say a lot about processes in this video and in following videos because they're a very important part of any system. Your program is a process when it's running. A Unix system will usually have a very large number of processes in memory at any one time. And typically a small system might have more than 150 processes. And when I say a small system, I mean something like a Raspberry Pi, a very small device with a small amount of memory. It'll still have a lot of processes or programs in the memory at any one time. Now, it might only run one of these programs at a time because there's only one CPU. In larger systems, there might be multiple cores, in other words, multiple CPUs, and so it can run several programs at the one time. But I'm going to assume we've only got one core, one CPU. Now, we can find out what processes are running with the PS command. PS, which stands for process status, allows you to get information on all the processes or a subset. Here we only see processes belonging to the logged in user. And I'll discuss how we get user IDs in a moment. The PS command can also display more information about running processes. When a process is running, it has an associated user identification number or a UID. This is used in many places in the system to indicate ownership of some resources. For example, it's used in the file system to indicate the owner of a file or the owner of a directory. The PS command maps the UID, which is a small integer, onto a name using a file called the password file. And this is stored in /etc/password. Entries in the password file look like this. Each entry is a line of text. In this one, 1000 is the UID. And /home/pi is the home directory. This example comes from a small Raspberry Pi system running Linux. We also see the shell that it's using, that's /bin/bash. And so when this user logs in, they'll be given that program as their shell program. The user ID or UID is used in many places in the operating system. The owner of a file is specified by UID and associated name, and the ls command, which is short for list, lists files, but it looks up the password file to associate the UID, the number, with the name. As well as UIDs, we also have group IDs or GID. And these are defined in the /etc/group file. Here we've got a mapping of the GID onto a group name, very similar to the password file. When a new account is created for a new user, it gets both a UID and a GID with the same name. The entry in the /etc/group file can also contain multiple user IDs for a single group. So for example, this one, which shows a group called audio with its associated number 29, and it's got two members. There are two users, Pi and Pulse are both members of that group. That's because we can give a file or a device a group owner, and therefore Pi and Pulse would be allowed to access this file that's in the audio group. Now, since files have both an owner and a group owner, they also have separate permissions for the owner and the group. And these permissions of what you can do on the file are either read or write, or in the case of a binary executable file, execute, or if it's a directory we're talking about, the last bit allows you to search the directory if you've got that permission. And these are given for the owner and for the group owner, in other words, everybody who's in the group, and for anybody else. So, for example, if you look at this example of an ls using the -l parameter, L for long, gives us a long listing of what's in this directory. And you can see I've only got one file here, my file, and it's got permissions for the owner, the group, and other. And you can see them here. The first, or the second, third, and fourth characters, RW- mean that the owner can read it, they can write it, but they can't execute it. And the group, anyone in the group can read it, but not write it or execute. And other, anybody else can read it, but not write it or execute it. And that's what those three groups mean. You can see where it's got the words pi. That means that it's both the owner of the file and also the group, the pi group. Lastly, we've got the creation time of the file and then the file name itself. The very first dash there, which I skipped over on the line, is an indicator of whether this is a directory or not. So if it's a D, that means it's a directory. If it's a dash, it's a normal file. And there are a few other designators for devices, B for a block device and C for a character device. Now, while we're on UIDs, I should mention the very special user ID of 0, right, the number 0. And that an owner or a process who is running with that owner of 0 is very privileged and can access any file and run any program, basically do anything at all in the system, overrides all the other permissions. And since devices are files in the namespace, it means you can access any device. The user with this UID of 0 is called the superuser or root. And the system parameters, how we configure our system, are all stored in files that are owned by this UID of 0. And that means the superuser can reconfigure the system by editing those files. It was given the name root since the very first process that's started by the system when the system is booting up is the root of a tree of processes. Each process can start multiple children or child processes, and in turn they can create child processes and so on. And the very first one is the root of this tree, and that's why they called it the root user of the system. The superuser, the root user, can also terminate any running process. So basically the superuser is all powerful, and therefore you should be very careful when you're using it. It can be quite dangerous. You might accidentally delete something or kill a process you didn't mean to. So just beware when you're logged on as the root or superuser. In fact, because the superuser is so powerful, the shell changes the prompt to a hash sign to indicate that the current user is the superuser. Now, from the shell, you can find out the user ID of the current running program, the shell, in other words, using this command, ID, just stands for identifier. And you can see here I'm running as the owner pi, or the user pi, and it has a user ID of 1000, a group ID of 1000, and it's in a whole series of groups. I've truncated it here because it didn't fit on the slide, but you can see that it's a member of pi, which is the same as the user, and it's a member of various other groups, and there's audio that I showed you before. Now, you know now that files have a number of associated attributes. They have names, they have an owner, they have a group, they have access permissions, and they also have a place on the mass storage, and so on. And all these attributes together we call the file metadata. A program or a process can access a file using the open system call. And what happens when you make a system call is your program is suspended briefly while the operating system kernel does the operation you specify. So in the case of open, one of the parameters is the path name for the file. So it goes and it finds it in the file system on mass storage, and it sets up a data structure containing all this metadata. The data structure also shows where your program is up to when reading the file sequentially. In a running process, this file data structure is referred to by a file descriptor, which is a small integer. When a program is started, the process is automatically given 3 open files and associated file descriptors. They are 0, also known as the standard input file, 1 for standard output, and 2 for standard error. Now, normally, these are connected to the keyboard for the input, the screen for the output, and screen for the error file. That's if you're running the program from the command line. Now, these standard input, standard output, and error files can be redirected in the shell using the following notation. If you have a less than for standard input, you can ask that the standard input doesn't just come from the keyboard, but comes from a file. Or greater than for standard output. So you can direct the standard output instead of to the screen, you can direct that to a file. And lastly, for the standard error file, where you write error messages, we do it in the following way, with a 2 and a greater than. And more generally, if you put some number, a small number, then that particular file descriptor will be redirected onto a file you specify. Now, this is done inside the kernel by using that metadata data structure that I talked about earlier. So that in that data structure, it shows where file descriptor 0 is going to be directed from and where file descriptor 1 is going to be directed to, and so on. One of the great inventions in the Unix operating system was the ability to create a special file called a pipe at runtime. And this has the property that whatever you write into this file, this pseudo file, was available for reading without it being stored on the mass storage. In fact, it's stored in the memory in some buffer space. If this pipe data structure or file is shared by 2 processes, one process could write the data into it and the other process read from it. And that way you set up a communication path from one process to another. In other words, you've created a pipe from one process to the other. The shell has a special syntax to let you create pipes between commands. And this uses the vertical bar character, as you can see in this example, and you create a pipe between the 2 running programs. So here we are, I've got a very simple command echo, echoing the characters hello, into a pipe with that vertical bar, into the WC or word count program, and you can see word count is counted. The number of lines is 1, the number of words is 1, and the number of characters is 6. Now you might count the characters in the word hello and say, wait a minute, there's only 5 characters there, but in fact there's also a new line at the end. Echo attaches a new line, so that's why it says 6 characters. And the nice thing about this is that the shell does all the hard work of setting up the pipe and its file descriptors. Your program simply writes to standard output. But in the shell, because of that pipe symbol, it will redirect your standard output to the pipe, and with the WC command, it will redirect its standard input from the pipe. And that way, the 2 processes can be made to send data from one to the other without them actually knowing that this is going on. Now, going back to an earlier example, if we want to find out how many processes are running in our system, we can use the ps command, right? And that will show a line for each process, but then we'd have to count all those lines manually. Instead, we can really easily just pipe the output of ps into the word count, WC command, and find out the number of lines and therefore the number of processes. You can do it like this. See, I've used the ps AX with the AX parameters. That gives me some extra information about all the processes. I've piped it into WC, and I've used the -L here, which says only print the number of lines. And there we are. This little Raspberry Pi is running 153 different processes. Now you might wonder, how on earth do I find out about these parameters to these commands? Well, remember in an earlier video, I talked about using the man command. If I was to type man ps, it would give me all the information I need about the ps command. Or man wc would tell me all about the wc command, and that's how I can find out about these parameters like AX and -L. Another major innovation in Unix was to make access to devices the same as any other file. All devices have a name in the namespace, and you use the standard open, close, read, write, and delete system calls to interact with them. And they do almost the same as they do for normal files. So, for example, on a typical Linux system, you might have this file, /dev/sta. And that's normally a path name that refers to a disk drive. The convention is that we put these special files into the namespace in the /dev directory. And sta is just a typical name for a disk drive and or part of a disk drive. And by opening and reading that particular file in the namespace, we can access this device and we can read from it. If we look at the details here with an ls command, you can see ls -l gives us more information about the file. You can see that it's readable and writable by the owner and by the group, but not by others. And its owner is root, the superuser, and its group is disk. And so we can make other users allow them to access the disk group and therefore access this device. Notice the very first character here is a B, which indicates it's a block device. If it was a D, it would be a normal directory. If it was a dash, a normal file. In Unix, all devices are accessed this way in the namespace. And this makes it very easy to write programs, no special system calls, just use the normal open, close, read, write, and so on. Other systems, such as Microsoft Windows, use special names for devices like C:, and so on. They're not in the same namespace. Now, when this device file is opened, the operating system looks at the file metadata and sees that this is not an ordinary file. All right, there's some indication in the metadata that it's one of these block devices, and it will pass the request to an appropriate device driver. Now, the device driver is a module of the operating system kernel that manages that particular type of device. For example, a disk drive or a network interface. And you can see the device type in the ls-l command. Looking at this output again of the ls-l, you'll see those numbers 8 and 0. Well, they tell us the major type of the device, that's the major number, 8, and the minor number would be the particular device. So it's a disk drive, so it'll use the disk driver module, and it's 0. As well as device files, the namespace can also specify pseudo files that, when opened and read, return information generated by a driver. So they're not actually mass storage and they're not actually devices, they're simply information that's returned by the driver. So, for example, on my Raspberry Pi system, the /proc/uptime name in the namespace or file will return the amount of time that the system has been up and how much idle time it's had. So, for example, this command, if I just do cat, remember cat copies a file to standard output, cat/proc/uptime, you can see the number of seconds that the system's been up and how much idle time there's been. Now, files in /proc, they're not device files, they're serviced by a driver for that particular service. Now, this is a really useful attribute of Unix systems, and if you go into the /proc directory, you'll find there are many files there which are really just services. And you can find out all sorts of information about running processes and other aspects of the system by reading one of those files. So Unix doesn't need any special system calls to find out these numbers. It just uses the ordinary open, close, read, write, but on a special name in the namespace, and therefore invoking a special driver to give the information back to you. So in this video, I've talked about processes and aspects of processes like user IDs and group IDs, and also how they relate to files, file ownership and file access. I also introduced the idea of a pipe, which is a very special file for connecting processes together. and devices being in the namespace. And lastly, I introduced the idea of services in the namespace with information produced by a driver.